In this video, I want to talk about memory allocation schemes. Basically, how do we decide, what little chunks of memory do I use for my program? Again, right, keep in mind we're doing this contiguous style. So I have kind of two methods for this, right? And my goal, right, somehow is to partition my memory, right? I can do this kind of with a constant sized areas and then also with variable sized areas. So I'll kind of draw a picture here for you guys. So what does constant size mean? That means the following, right? So I have my memory layout picture again, and I'm going to carefully try and divide into even sections, right? So the idea is that if I have some amount of space available, right? So it's like I know ahead of time, I have 4 gigs of memory installed or whatever. Well, I can basically say, this is going to be 1 GB, 1 GB. I can basically break into equal spaces, right? So they're all going to be basically this one constant size. So that's one scheme. And that's kind of what we had implied on the other side, although it's not the only way to do it. The other thing we could do is have a variable sized partitions. So what that looks like is basically I'll draw another picture here, right? And here, right, we'll say, I have a little tiny one here, then maybe 2 bigger ones, right? So maybe I have, a 0.5. The units of these are all, something like GB, right? And then 1.5, 1.5, right? So the idea there, right, is that basically I have these different size, little indices here, right? Instead of saying they're all the same, I can say that they're, variable sizes. And this one, right, maybe you can guess this is going to be kind of the better choice overall. Simply because it gives us more flexibility. Because you can imagine, right, if I have a process that reserves, this 1 GB and all of a sudden it only uses, half of that, well, I've wasted a bunch of space. That causes what we refer to as fragmentation, and we'll come back to that in a few minutes. So over here, right, this is kind of a better scheme, right, kind of, is a little bit more adaptive, right? We can even think about maybe resizing these things as we go. So yeah, these are our two all ideas here. Here we can either have constant size partitions or variable size partitions. Now, when I have a space in memory that is vacant, I'm going to call it a hole. And so here, right, in this picture, just a couple more processes here. This is a hole. This is a hole. I have 4 holes in my diagram there, right? A hole again just represents a kind of a memory partition, right? That no process is using, right? So it's a hole. It's something that I can basically add something to. And so the idea, right, is that a program is running, right? What happens is, right, I basically need to somehow have some method to go and find a hole that has enough memory, right, for that process to run, right? So I need to basically do an allocation. So process is running, do an allocation. All of a sudden, right, I'll find that hole for that process, right? Put that process in there. And the inverse, right, is basically, if I have a process, right, that needs to terminate, right, then I'll release the memory, right? So I create a hole, right? So processes go into holes and they come out and they generate holes. I always wonder where this terminology comes from. It sounds a little bit weird to me. All right. So some notes here, which are really going to be kind of specific to the partition methodology here, is that we can have maybe a little bit of flexibility, right? A little bit more flexibility, right, if we're allowing this variable size. And so what happens, right, is let's say, during allocation, for example, right, I may have my little intervals here, right? Well, if it happens to be the case that I do an allocation, right, I try to put a process in a hole, and that process is actually smaller than that hole, what I can think about is, I'll just, kind of resize my divisions. So here, right, P1 needed less than that, right? Initially, I had drawn this as kind of one whole thing. P1 needs less than that. Well, put P1 in, and then basically, split it, right? Make it a smaller partition, right? So I can basically size things to how I want. And then if I size things to how I want, I can also think about basically, making holes bigger. So it's like, well, maybe I just have something like that, right? That bottom hole kind of absorbs the half that was left over by that P1, only using half of the hole I initially assigned for. Right, so it's almost like you can think about these, these little boundaries, right, as being changing, right? So we maybe start with some picture that looks like this, and based on how processes are either added or deleted, we kind of add more segments, right? So if we delete a process, typically that means we reduce the number of holes, right? Because we can just kind of like cut a berry out. That's what I did over here in this picture over here. Or, right, if I add a process, well, then I need to do a cut, right? I need to kind of cut somewhere, and make a little partition that's just the right space for this process. So I can do that, right? So those are kind of ways I can kind of manipulate my memory a little bit. All right, so we have the constant scheme, we have the variable scheme. Let's talk a little bit more about basically the selection of holes. So this is one thing, right, that we're definitely gonna have to worry about. We have to worry about, I'm running a process, how do I pick, what holes should I fill in? And I have 3 different choices here. So I have best fit, first fit, and worst fit. And I know it's funny to say worst fit because it's like, well, why do I do the worst fit? But we'll see in a second. So the first one, right, is basically first fit. So the implication here, right, is that you have sort of a list that represents all of your holes. So you can imagine, right, you have your program right over here, right? Maybe you have, 3 different holes, right? And all of a sudden this corresponds basically to a linked list that says, I have, 0.5 here. We'll just do this. I know it's not quite to size, but we'll pretend it is. And we have some sort of a list, right, that basically is going to store inside of it, these are the things that are available. So this is, something that's there I would have in kind of my OS is managing. So I have that there. And the thought for this first technique is, well, if I get asked to allocate memory for a process, just go on along your list, and the first thing that has enough space, use that, right? So it's like if I request, a 1, what happens is I end up picking up this one, right? That would be basically the first thing in my list that, can fit a size 1 program. If I have a size 5, well, then I'll go ahead and do this one over here. So even though I have multiple holes that kind of are that appropriate size, I'll just end up using kind of the first one that I see. So this is kind of the first fit. So this is one way to do it, and this is okay. It'll work, but we can do a little bit better. The next idea, right, is basically to look at what we'll call a best fit. So let's say, right, that I have a process of size 0.4. That probably would be a fair one. So let's go. We have a process of size 0.4. Basically, what it means is I'm going to search for the hole that is kind of the one that's the closest in that, right? So I want to find something that's as close to 4 as possible without being too big or too small. So in this case, right, I can definitely store 0.4 into 0.5 or into 0.1, right? But I want kind of that one that's closest to me, right? I want one that's the smallest without going too much larger. And so in that case, right, I would match my 0.4 to my 0.5, right? So this is my program. And then, so this is my program. It's supposed to say program, guys. It's supposed to say program there. So I want to basically take my program, right, and map it to available memory, right? So this is my memory over here. I'm trying to find some place to spit it in, right? I could put it into 1. Doesn't really make a lot of sense, though. Best fit means find something that's closest in size. So I'll put the program there. If I have something of size 0.9, obviously it's got to go to a 1, right? If I have something like a 0.3, it's also going to go to that 0.5. 0.2 is going to go to that 0.5, so on and so forth. So what is the best fit? So that's fine, right? And this is even, maybe relates back to the previous idea of we can resize things. So if I, create a hole, next to something that, or is a hole where I can maybe expand the first one, right? That's something maybe I can think about doing. The other thing here, right? This is the final idea we have, is basically this idea of a worst fit. So actually what I should do here is let's make a little table, for example. So let's say we have a process of size 4, process of size 0.5, process of 0.8, right? So in best fit, right, basically 4 goes to the first one there, 5 also goes to the first one there, then 8 goes to this one, right? That's how our best fit looks. Now, in contrast, right, if I were to do maybe my my worst fit, this is how the mapping would look. The idea of the worst fit is basically I'm going to put your new process program into the kind of the space that's biggest, which is kind of a little bit counterintuitive. So here, right, if we have something at 0.4, 0.5, 0.8, basically these all map to the one space of 0.1, right? Even the small ones, right? So even 0.4 and 0.5 they all end up kind of going to the same middle space there. The idea there is if I put something small in there, right, and let's say I have a little chunk here, right, that I kind of like, oh, that's the 0.4. If I have I basically introduce just a little sliver, right, and I leave that 0.6 free. What happens is, by the previous ideas, we just absorb that into the next hole, right? So it's like, well, I'll delete that little marker there, right? I'll also have a bigger hole. So the hope with that worst fit is basically you're going to grow the holes next to it. So it's a little bit different, right? So even though I know it says worst, it is still pretty good, right? So both these, best fit and worst fit, those will have kind of decent performance. So there you have it, right? Those are 3 different schemes for basically picking where in memory your program should be stored.